David, do you want to fix some of the lights?
Oh,
Thank you. So today I'll just be sharing with you a story about impact cratering, very general in the solar system. Brief outline. First we'll talk about what is an impact crater. Why should we care about impact craters? And then we'll go through some things that we've learned from studying impact craters in the inner solar system and then in the outer solar system, and go through some quick conclusions and talk about some questions that still remain about studying impact craters. So, what is an impact crater? Well, it's just basically a hole in the ground. We see two examples here. One is Barringer Meteor Crater, which is on the Earth in Arizona, and you can go see it. It's open for tours and such. And then this is a much larger crater on the Moon called Bessel Crater. So, more important thing is what creates impact craters, or how do impact craters form. At first, they weren't even necessarily thought to be from impacts. They just knew that they were depressions in the ground. The first observation of this was by Galileo, who just saw circular features on the Moon, and realized from the shadow interactions as they moved through the terminator that they were depressions. And like I said, for quite a while, for about 200 years ago, many think they're volcanic features because they look similar to extinct volcanoes on the Earth, a lot like calderas. And some have even claimed to see volcanic eruptions on the Moon. And the other reason was that they pretty much thought space was empty except for the big planetary bodies or satellites, because the idea of meteorites was not verified until the early 1800s. However, as we were approaching the turn of the century, into the 1900s, they did finally realize that, of course, there were meteorites, and that they might hit bigger bodies, such as the Moon. And by looking closely at images and through the telescope, they found, with some geology and doing experiments, such as just basically throwing or dropping a sphere into sand or into mud, that they saw that these would form holes in the ground. And so it was in about 1893, there was the first serious support for that lunar craters were formed by impacts. And about the same time, they realized that the Barringer Meteor Crater, which we saw in the previous picture, was also recognized as created by impacts, basically through a couple lines of evidence. One, they saw unusual iron remnants, and they figured that this might be some kind of iron meteorite that impacted the remains of that. And then they also saw that the layers of the sediments around the impact were kind of up-tilted, and at the edges were actually kind of flipped over, which they thought might have been material thrown out from the crater. And they already understood a bit about this from explosions and such underground. Finally, in 1916, OPIC determined that these impacts were high velocity, which basically but the idea that many of the craters that they saw were circular, and a lot of the experiments that they were doing were at very low velocities. And so if they changed the impact angles from vertical at all, they would suddenly get elliptical craters. But if you come in at very high velocity, you actually get circular craters at most impact angles. So this basically led to the thought that we believe today that impact craters are generated from high velocity impacts. And hopefully this will run. So this is just a little cartoon going through what happens during an impact. Basically, the meteor comes in and slams into the body and starts digging a hole into the earth and throwing out material and such. So, what is the physics behind impact cratering? Well, we need to understand how the stress or shock waves propagate through the material in three stages. The first is through contact and compression, where the projectile first hits the surface of the body. And then you have excavation, where the stress waves are moving through the body and actually bouncing off the interior layers and coming back and causing material to be thrown out. And then you have modification of the crater as the last step, where it's basically just gravity starts pulling on the cavity that is created, and things start to slump and change. This is a very broad overview of what happens during impact. In this book right here, Impact Cratering by H.J. Malash, gives a very detailed description of what occurs during all these processes. But to basically kind of sum it up, there are 3 equations used to describe the shock fronts of impacts that use conservation of mass, momentum, and energy across the shock discontinuity that were derived back to 1887 by Hugoniot. And so they are called the Hugoniot equations. And they basically allow you to relate pressure, the shock velocity, the particle velocity behind the shock front, the specific internal energy in front of and behind the front, and the specific volume through these equations, so you can calculate what the states might be as the shock is moving along through the body. However, in addition to truly understand what's going on, you also need an equation of state in addition to these that relate the pressure and the volume. And this equation of state is dependent on basically the properties of the material that's being shocked, the rock and such. And it's actually not derivable from first principles, and is mainly, we know about it through experiments such as these. Large explosives, basically they set off explosions just under the surface on the Earth here. They even use, they've even looked at some of the craters left behind by some of the tests of the nuclear explosives. You have laboratory simulations. This is the high velocity gun at NASA Ames, and this is a movie of one of these particles being shot into a test surface and forming an impact crater. And then when computers came around, you can have numerical simulations. So through these, we have a better understanding of the physics behind impacts, and what kind of information you need to know about the materials, so you can really work out the equations and such. Before getting into some of the results, I just need to quickly describe what the crater morphology terms are. We first have simple craters, which are the smallest of the craters, and they are basically just usually circular and bowl-shaped. Then you have complex craters, which generally have flatter floors. They will often have a central peak or central pit, and sometimes even a peak ring. So this one is a central peak, and sometimes you might have a series of these peaks that just forms a ring instead of a central uplift. And these occur for slightly larger impactors. And for the largest impactors, you get what we call multi-ringed basins. And this is an example of one. This is Orbital on the Moon. And basically, the impact just generates so much energy that you start just fracturing the crust in concentric circles around the impact. And finally, these are all from primary impacts, so impacts that are coming in from outer space and hitting a body at high velocity. But you do have another kind of impact on the surface, and that's from secondaries, which are generated from the ejecta that's being thrown out when the primary hits the surface. And these generally form simple craters that are in the simple morphology, but they usually are shallower than simple craters that are formed by primary impacts. And they often are elliptical and form in these clusters because the ejecta all kinds tend to clump together as it's coming away from the primary crater. So why should we care about impact craters? Well, first of all, primarily because they are found on every solid planetary surface except Jupiter's moon Io. So they are a primary part of the geology of almost every planetary body and satellite and dwarf planet that we have imaged with the degree to see these kinds of features. So here we have an example of impact craters on Mercury, Venus, Mars and the asteroid Eros. And I've already shown some examples of impact craters on the Earth and the Moon. And we also see them in the outer solar system. This is Jupiter's moon Callisto, this is Saturn's moon Rhea, and this is Uranus's moon Titania, and this is Neptune's moon Triton. And although this is a fairly actually young surface, and in this image we can only see one impact crater right over here. So, what can studying impact craters tell us about these surfaces? Well, first, it can tell us a little bit about surface processes. Although there are many features on these on planets that have volcanism to tell us about the volcanism, something that impact craters can tell us is maybe how deep a lava flow is, because we generally have an idea from the physics previously introduced of how deep an impact crater should be depending on its diameter. So we might be able to determine something like that. Or exactly how far the volcanism has embayed into some of the craters and such. We can also find out something about tectonics, as we can see from these so-called strain craters on Jupiter's moon Ganymede. When a Robin or a tensional fault intersects a crater, you can use what is the assumption of the original crater shape to maybe find out how much the terrain has been separated by this tensional fault. Might also learn a little bit about erosion, maybe about how fast it occurs, because we have a general idea of how a fresh crater should look. It might also tell us something about some unique types of erosion that are going on in our solar system. For example, Jupiter's moon Callisto has these, which we'll talk about later, has the crater rims, which are topographical highs, kind of being formed into individual little mountains as the surface is eroded, and this is kind of a process that's unique to Callisto. They can also tell us something about the interior. Since craters are basically holes into the ground, we can look into them and see what the crust looks like below the surface, and this has been especially important on Mars, where all we have right now are the rovers that go in, and they can go into the craters and look at the crater walls and see what the layers look like, and some of the layers have shown evidence for possibly water sitting in these craters or running through the craters, or if not water, maybe just very high ice-rich. And the ejecta, which is thrown out, which is basically material that used to be buried, is now on the surface, can also tell us something. For example, on Mars, we see many of these craters that have these kind of fluid-like ejecta patterns. And this is thought that this occurs because this might have been a ice-rich or water-rich area when this impact was formed. Might also give us clues about the deeper interiors. For example, on Jupiter's moon Europa, we often see these large multi-ring basins that are flat and form many, many fractures from the center of the impact. And this is likely caused because of an impact into a body that has a very thin ice crust that's brittle, but the interior underneath it is likely either very warm ice or even water, and so it's almost, you can almost think of like punching a hole through a thin ice layer covering a lake, and then the water, if you get the water to come up and freeze again fast enough, which happens on these bodies because they have no atmosphere to keep them warm, they're basically exposed to space. You can just kind of see how this might cause these fractures and then cause a very smooth surface in the center where the water or the warm ice has come and immediately froze. You might also be able to learn something about past heat flow or current heat flow from the fact that many of these craters often, especially on the icy satellites, become relaxed with time as they get older. Basically, relaxed just means they start to lose their topography as the material that's holding them becomes warm enough that it starts to kind of flow, but very slowly. Might also be able to learn something about solar system dynamics. One thing is I don't know why that happened.
Okay.
So one thing you might be able to learn about are breakups. When Voyager first went out to the Jupiter system, we saw these features that are called Cassina, which are basically linear crater chains on the surface of Callisto and on Ganymede. And scientists proposed that these were likely due from comets being broken up by Jupiter's gravity and then impacting onto the surface. Well, this was verified when Shoemaker-Levy 9 passed by Jupiter and, of course, eventually hit Jupiter. But we saw that before it hit, it was broken into a long linear chain of smaller impactors. The comet was broken up. We can learn something about what maybe the impactor population and what the impact rates have been through the solar system. This just shows a plot of impactor diameter versus asteroid diameter, which shows that from the basic physics we talked about, you can determine how large the impactor was if you know the diameter of the crater. And so then you can back out what the impactor population must look like if you look at the crater population on the surface. And if you can age what that surface, you might be able to know, especially if you have surfaces with different ages and you know the density of craters on those different surfaces, and you can relate them back to an actual age, possibly through radiometric dating like we have on the Moon or Earth. You can get what the impact rate has been through time, or maybe just in one time, but hopefully you can get a wide range. Something else that's possible is orbital dynamics. In other words, how has the orbits maybe of the planets in our solar system changed with time? One evidence of this is that on the Moon, scientists have discovered that many of the large basins are all about the same age, they were all formed about 4 billion years ago. And this is called the Lunar cataclysm, or late heavy bombardment. And scientists often wondered, why would we all of a sudden have all these impacts occurring at one very short time period, and especially almost 500 million years after the Moon should have formed, when we think the heaviest bombardment should have happened. And so they began to run numerical models such as this, which, if it arcs, there we go, which just basically follow the dynamics of the asteroid belt and the inner planets, and what we're not seeing is what Jupiter and the other gas giants are doing. And as their orbits might change, you basically get the asteroids being, if a certain change happens, which they believe did, then you suddenly get the asteroids just being thrown everywhere all throughout the inner solar system. And
Resonance.
Yeah, basically, you get into specific resonances. Finally, we can look into the historical geology and possibly date the ages of the surfaces throughout the solar system by using impact craters. One way is through stratigraphy, which basically means that you're looking at superpositions. So when one crater falls upon another, you have to figure that it's younger and that the other crater is older. You can also use this on other features, such as if you see them on top of faults, or if you see them on volcanoes, then you can use this to at least help you relatively date when these processes happen on the surfaces. You can also use a little bit of morphology. Like I mentioned earlier, erosion will start to degrade a crater over time. If you know a little bit something about the erosional process, you might be able to get an idea of how old this fresh crater is compared to this degraded crater. And final way to do this is what my work primarily focuses on, which is crater counting. And while it doesn't sound very exciting, it can tell us a lot about what's going on the surface. So basically, through time, we have the impacts building up and building up. Start. Not. Okay. So we have the impacts building up over time, and as that happens, you can look at how many have formed on the surface of a certain diameter, and you might be able to back out the time of that surface. So, for example, here's an area of Dione that I have actually counted. So I had to first map out an area that would give me the best results. So in other words, that was the imaging was good enough that I could identify the craters. And then I basically counted those craters and found out how many there were, and of a certain diameter. And then from that, I can hopefully back out how old the surface is. The biggest unknown in this is actually what the impact cratering rate is for the outer solar system. Dione is a moon of Saturn. And so we'll talk a little bit more about that later. So what have crater studies told us about processes in the inner solar system? Well, we'll start with Mercury. This is a image from actually Messenger, which is flying by Mercury. This image just came down in January. In the past, we had another flyby of Mercury from Mariner 10, which was in the 70s. And actually, Messenger is eventually going to start orbiting Mercury, so we'll hopefully get lots and lots of data from that. But even from Mariner days, we knew that Mercury was heavily cratered. Basically, every part we looked at had lots and lots of craters. But we do see that some material bathes and fills craters, which you can see a little bit in this image, with some of these just being almost ghost images of craters. And this may be evidence for volcanism, but some also argue that it just may be evidence of the fact that impact ejecta can be very efficient at burying old craters. So if you have a lot, if this is a particularly old crater, which it probably is, and it's surrounded by lots of new craters, it can be eventually buried by impact ejecta. We see some tectonics that disrupt craters. So we might be able to get an idea again of what kind of tectonics have occurred and how much movement there has been. We find that younger craters in general have kind of a bright ejecta and bright floors, which can be seen by this example here. And mainly what this is telling us is that below this darker kind of surface, there is some kind of brighter material that's been either buried, or the dark may just mean that it's been altered in some way. But anyway, we get an idea of what this material looks like as it's fresh and new. So we might get a better idea of what Mercury's crust is actually made of compositionally. We find that Mercury in general is an old surface. Here's a plot of what crater counters commonly call the R value, which is basically just a ratio of the actual density of the craters at that particular diameter to an idealized density. Basically, it's based upon what the density is on the moon. And outlined in red, we have a crater counts from what's considered basically the oldest area of Mercury. And in blue, we see an area that might be actually slightly younger because it has a lower density of craters. But overall, even this is still pretty heavily cratered, and we don't think that it's all that much younger than the terrain represented by these counts. It's been found that the degradation of craters occurs faster on Mercury, and this is likely because than it does on the moon, and this is probably because of the fact that the gravity is higher on Mercury, and so it's making the ejecta blankets, rather than flying out very broadly over the surface, being very tight and clustered. So like we talked about up here, they can bury the craters and remove craters faster. And then the transition diameter, or the diameter at which we have simple craters becoming complex craters, is the same on different terrains on Mercury. So if you go from maybe this older terrain to this younger terrain, the diameter at which craters start to become complex rather than simple is the same. And basically what this just tells us is that the composition is fairly uniform, because that's what this factor is generally most dependent on, at least on one surface. It's dependent on gravity, but that only hopefully changes from planet to planet and not on a planet itself. So on a planet, it's mostly dependent on the crustal properties, the strength of the material. And so this is telling us that it's pretty uniform through the whole surface of Mercury. Okay, so Venus overall is actually very lightly cratered. We've had a few missions go to Venus. Some of the bigger ones have been Magellan in the 90s, the Venera landers, which were actually Russian in 1982, and there's a mission from Europe called Venus Express that's currently orbiting Venus. And all these images are actually from Magellan, and they're all radar images because that's the only way we can get a good picture of the surface because of the thick atmosphere around Venus. But again, we find that materials invade and fill some craters, as can be seen by this dark material on the interior of the craters. The ejecta is bright because it's rough, and in radar, rough things are bright, and smooth things are dark. So we think this is smooth material. On Venus, unlike Mercury, it's most likely that this is volcanism because we see many other features, such as shield volcanoes, that are evident of volcanism on Venus. It seems that the craters have been not been eroded very much, and this could either mean, one, that erosion isn't very effective on Venus, or that these are all fairly new and fresh craters. I have a feeling the second is probably a little bit more likely because Venus, with its atmosphere, is a very least windy, dynamic planet. The craters, like I said, there's not very many craters, and they seem to be scattered pretty randomly across the surface. And using lunar chronology, so we're using the fact that a certain density of craters on the moon means a certain age. They have dated the surface to be about 500 million years old, and that's the whole surface. And this, the idea that they're scattered randomly and don't seem to be preferentially more densely cratered on one part than another, likely means that, one, that Venus was resurfaced globally in one big event about 500 million years ago, or that there has been spurts, but they've been evenly distributed all over the planet and have been actively destroying craters everywhere, but it's not necessarily one big event. We find that there's no small craters, which is due to the atmosphere breaking up smaller bodies. We find dark splotches, which are probably evidence of disruption of meteorites in the atmosphere. And here's an example. In the bright material in the interior might actually be remnants of the impactor that, as it was slowed down, it just kind of plopped onto the ground. And then the dark splotch is just disturbed terrain from the wind of the explosion just above the surface. Many of the craters have the big white area around here is actually ejecta fallout. Probably some of the lighter material that's ejected this is the main ejecta blanket. But they have this unusual parabola shape, which is likely indicating wind patterns. So basically the wind was blowing from this way. So as you think of wind blowing smoke, basically it just did the same thing and it made it fall out in one particular direction. Again, we find tectonics disrupting craters. And it's typical that the craters on Venus do not seem to be viscously relaxed, as we talked about for some of the craters on the icy satellites. And this means that the crustal thickness, they can back this out from that idea that it has to be about 10 to 20 kilometers thick. As we know, the Earth is actually very lightly cratered. There's only about 150 known craters on the Earth. So activity on Earth is very efficient at erasing craters. Plate tectonics does it well. The volcanism and sediments deposited from water runoff and such. And like Venus, Earth's atmosphere affects impactors. It breaks them up. It keeps small impactors from coming in. We've had airbursts. One that was in Russia, the Tunguska airburst in 1908, which basically flattened a whole forest from the wind created by the explosion. We can study, because we're here, we can study what impacts due to planetary bodies and life forms as well. A famous example of this is the KT boundary extinction, which killed off the dinosaurs, has been related to an impact crater called Chicxulub, and that's off the Yucatan Peninsula. And so this is a nice artist rendition of what it might have looked like to the dinosaurs that were near the impact anyway. It wouldn't have looked like this everywhere, but and eventually it created fires and cooled the Earth off from the debris that got stuck in the atmosphere from the ejecta. So it can be big enough impacts can be very good at possibly destroying life on Earth, and if there's other planets with life, that could be a threat for them as well. Impacts bring up deeper rocks. They not only create holes, but the ejecta is made of material that comes up from depth, and if there is a central peak, the central peak is generally material that's uplifted from depth. And so you could study rocks here on the Earth that you might not otherwise be able to get to without either drilling very deep holes or doing seismic studies or something like that. Something else we can do on Earth, because we're here, and is explore the compositions of impactors. As I mentioned, one of the things they found at Barringer Meteor Crater was remnants of the impactor, this iron meteorite. And so in many of the craters, they can find just little bits of remnant of the impactor that came and formed that crater. So it's helped us learn something about meteorites and these bodies that have formed the impacts. And we can study the effect up close of what the large stresses can do to rock and materials. One example is what it does to the mineral quartz, which this picture on the left is a version of unshocked quartz, and after an impact occurs, this is what happens to a quartz crystal. It develops these lineaments and looks very unique in it, and generally only impacts are strong enough to create features like this, so this is a marker of an impact. The moon is generally heavily cratered. There have been many missions to the moon. Apollo, where of course we sent men to the moon, was very exciting. The Clementine mission was an orbiter that orbited in the mid-90s. And of course we have hopefully men going back to the moon very, very soon, maybe 10, 20 years. Something we've been able to get from studying craters on the moon is what we think the cratering rate has been for the moon. And that's just because we can not only count the craters, but we have dates of specific areas on the moon that are related to specific impacts. And this is mainly from the Apollo mission, which of course brought back samples that we could form radiometric dating on. And so you can relate crater densities to actual ages of these places on the moon where they counted the craters. And so you can get an idea of what the cratering rate has been through time. So this is the age of the surface, this being 4.5 billion years ago, and then to the present. So we can see in general in the past the cratering rate was much larger than it is today. This would be the number of craters formed on any square kilometer. As mentioned previously, we learned something from the late heavy bombardment of the moon. So again, here's a picture of or a graph of some of the impact melts that have been dated. When they went to the moon, they got samples of a melt sheet that's caused by when the impact heats up the crust, and they dated these, and they found that most of the big basins again peaked at this age of about 3.9 or 4 billion years ago. And as mentioned, as shown previously, this movie shows that this late heavy bombardment might have been caused by the asteroids being dynamically scattered by Jupiter and the gas planets forming kind of a resonance that with the asteroids that made them really move around in the inner solar system and hit planets. We find that there's material that embays and fills some craters, and from analyses we know that this is the dark areas. We know that that's actually basalts, volcanic basalts. The crater distributions are different on the lunar highlands, which are generally the lighter areas, and the mare, which are the darker areas, the volcanic areas, which means that the volcanism was later and than when the crust of the moon was formed. Again, we see that often the ejecta seems to be brighter than the rest of the terrain. Again, telling us a little bit about what the interior might look like, or what the fresh crust looks like. We also see dark halo craters, which are actually evidence possibly for buried Maria volcanism. So basically the craters are throwing up dark basalt material onto the surface that was buried underneath the lighter material. And Mars is a planet that is lightly to heavily cratered. There have been many missions that went to Mars. This is just a few of them. We had the Mariners, which were the first, and then had Vikings, which were orbiters and landers, Pathfinder, which was the first rover to go to Mars. And right now we have the Mars Exploration Rovers and the Mars Reconnaissance Orbiter, which is getting some very high resolution images of the surface of Mars.
Was it scheduled to
I don't know of anything.
It's May.
May.
It's the European one.
Is it? Mars Express? Yeah. Okay, yeah. Yeah, there's, like I said, there's so many, I didn't want to put them all up here because that would be the whole slide. But yes, there's currently also Mars Express, which is the European mission. Cool. Again, they can look into what past crustal layers look like. Here's another picture from the MER rovers looking in detail at the side of this crater and seeing various layers, and they claim that they see evidence for water in these layers. The fluidized ejecta, as we mentioned earlier, is also another evidence for water. Pedestral craters are actually, which is shown here, are actually evidence probably more for that this ejecta was formed out of material deeper in the crust that is actually stronger than the material surrounding it, so it's not being eroded as fast as the surrounding material. And we see units with very different crater densities, as shown by this plot, where the red lines are from Mars, the blue is actually the moon. But you can see that we have some highly cratered units, and we have a unit that's less densely cratered. And this is actually part of the dichotomy of Mars, that we see that the south regions are actually more heavily cratered than the north regions, which are called plains. This seems to be evidence for faster erosion on Mars than on the moon, which probably makes sense because it has an atmosphere and has winds. And we again find in bay craters, and we already knew that Mars was volcanic from the big volcanoes, the Tharsis volcanoes and Olympus Mons. But again, the craters can tell us a little bit about maybe how thick the lava flows were. So just kind of sum up about the inner solar system and do some comparisons. Here's a plot which is comparing just a bunch of different terrains from the inner solar system. All the red lines are Mars and different areas on Mars. The green lines are Mercury, and then the blue line is the lunar highlands, or the oldest part of the moon. But what's basically about this is that the ancient terrains all seem to show a similar shape in their distribution here. So this again is just the R value, or the density of craters, versus the crater diameter. And they all actually seem to have very similar densities too, especially for these older terrains. And this implies that there has been one primary impactor population, and it's likely main belt asteroids. We've had enough imaging of of various sizes of asteroids in the asteroid belt that we have found that they have a similar size frequency distribution shape. That's just the term for this distribution. So that's a very nice connection. So we know what kind of bodies have created. We know that asteroids have created the impact craters in the inner solar system. This similarity also implies that the late heavy bombardment that occurred on the moon has occurred throughout the inner solar system and was due to the scattering of the main belt asteroids by orbital migration of the gas giants, which was shown earlier in those movies. The transition diameter, again, between the simple and convex craters is similar for Mercury and the Moon, but is slightly different than for Earth and Mars, implying that impacts can be different into dry targets, in other words, the Mercury and Moon, which are not thought to have much water, than targets that were wet, such as Earth and Mars. Again, showing that this transition diameter is affected by the material strength. We find that the ring spacing for multi-ring basins is similar on all bodies, implying that the target property is not an important factor for basin ring formation. Basin ring formation is basically just a factor of the amount of energy going into the impact, so the size of the impact and how fast it's coming in. And then through crater counting and age dating, we find that some bodies have been more recently active than others. Venus has been dated to be about 500 million years old. Mars' surface can be anywhere from 500 million to 2 billion years old. The younger terrains, the oldest terrains on Mars are basically the age of the solar system, 4.5 billion years ago. The Moon, the Mare on the Moon is about 3 billion years old, and then Mercury, however, doesn't seem to have any terrains much younger than 4 billion years old. So what can crater studies tell us about the outer solar system? Well, the outer solar system also has solid planetary surfaces, although they tend to be a little different. Most of them are made of ice, but they can be just as big or not even slightly bigger than some of the planets that we've looked at, or the other satellites such as the Moon. The only exception to being icy is the Jupiter's moon Io, which is actually also primarily silicates like the Moon. But it's also a moon that we're not going to talk about very much here because it has no impact craters found so far on its surface. And what this means is that it's a very dynamic little moon, and it's actually very volcanically active, and that these craters are being buried as fast as they can form. Well, we'll start with Jupiter's moons. So again, we have Io, which we're not going to talk about because it has no craters. We have Europa, which is lightly cratered and has been somewhat active. Talk about Ganymede here, which is lightly too heavily cratered. It has some terrains that are lightly cratered and terrains that are very old. Showing it had some activity, but not as much as Europa. And then we'll look at Callisto, which has basically had no activity. It's very heavily cratered and has no signs of having been resurfaced or even tectonized very much besides basins, big basins, the tectonics of big basins. So something Europa has been able. Okay, there we go. Something Europa has been able to tell us is that secondaries, which are the impacts formed by debris thrown out by the primary impacts, may be an important influence on the crater densities at smaller diameters. And this is an issue if you want to try and date surfaces with small craters. If you know what your primary impactor flux is and you know that it varies with time, but your secondary impactor flux does not vary in any way with time, or it can be very spatially inhomogeneous because of the fact that it's only formed by big impacts, and their sizes are also dependent on the size of the primary impact. So if you have these contaminating your counts of craters at small diameters, then these densities may not actually be informing you of what the actual age of the surface is. They would just be able to give you a maximum age of the surface. And something that Europa has told us is that we found that many of the craters on Europa, which is only lightly cratered by primary impacts, are actually secondary craters. So what might this mean for a body like the Moon, which is heavily cratered by all kinds of impacts? We see the strained craters on Ganymede, as already discussed. As mentioned, Ganymede's had terrains with different crater densities, indicating that activity has been occurring at different places at different times. Ganymede also has pedestal craters, like the Moon, or like Mars. I'm sorry. Again, implying something about the strength of crust and possibly what the interior of the crust looks like. Callisto has this unique degradation process and a lack of small craters. which both imply something about the material on Callisto's surface and how it is moved around. Basically, Callisto is an icy body that's covered by some kind of darker material. And the color contrast between the bright ice and this dark material and causes the different kind of sputtering erosion that moves the material and sublimates the ice as the sun hits the surface. So there's just weird, funny things going around with this material, and it might give us some clues about what this material is. They all have central pit craters, which we did not find in the inner solar system. Dome craters is basically a pit crater that has a little dome in the pit. And this might be telling us something about the difference between impacts in ice and impacts in rock. They all have different color material that's excavated by an impact crater. So again, we're seeing fresh ejecta from newer impacts that are different, either lighter or darker, depending on what kind of terrain they're on, than the terrain itself. Telling something about how the crust might be layered into different compositional layers. Some of the crater floors are level with the exterior terrain, and we have these furrows being formed. And this would apply large impacts, like I mentioned earlier, into a thin layer of crust over the ductile ice water, which is causing these flat floors and these multiple fractures around the crater. And again, we see relaxed craters on all of the surfaces, implying something about the heat flows in their past and the ductility of ice. So Saturn's moon are basically we have 8 smaller moons. Mid-sized moons is generally how they're referred to. And they can be lightly to heavily cratered. Enceladus is very lightly cratered and actually has evidence for activity. This is a close-up image of Enceladus. And then moons like Tethys and Rhea and Mimas and Dione are all a little bit more heavily cratered, and Iapetus as well. They also have relaxed craters, again telling us something about the heat flow. Here's a basin called Odysseus on Tethys, which is actually relaxed all the way back so that it follows the actual shape of Tethys's surface. We can learn a little bit about something of the energy required for satellite breakup. This is a very small picture of Mimas, but Mimas has a huge crater that makes it look like the Death Star. And it's not like this one on Tethys. It's actually there's a deep hole carved into the side of Mimas. But this crater, as large as it is, did not break Mimas up when it hit. So this tells us something about how much energy might be required to actually break up a satellite. On Iapetus, we see these white floored craters in the dark terrain, and dark material in the floors of craters in the bright terrain. And this is just giving us a little bit of clues about what the dark material might be and how it's related. Basically, we think that the dark material is a coating onto the bright white ice, but it's not very thick, because as impacts come in, newer impacts come in, they actually dig deep enough to get back into the fresh ice, so we see the fresh ice again. On Rhea, we found that the abundance of small craters is greater than on some of the other satellites, which might be implying that there is another impactor population in the Saturnian system that is just primarily formed from small impactors. And this has been hypothesized to actually be a debris that orbits around Saturn, which we know is there because of the rings. We see a relative decrease of larger craters on the younger terrains. Again, hint to this other impactor population that is just primarily formed of small craters. Again, we see some surfaces with a faulted and strained craters. Enceladus is a good example of this. And again, there are terrains of varying crater density indicating activity at different times and places on these surfaces. Just talk a little bit more about Saturn, because this is where my work is actually focused right now at the Lunar and Planetary Institute. I've been counting craters from the images from Cassini of these various satellites to do comparisons. And these are some of my results, again, in the R-plot format. And we see that in general for the heavier craters terrain such as Mimas, Tethys, Dione, and Rhea, they all again have a similar shape, implying that there's the same primary impactor population hitting these surfaces. In this data, I have yet to find evidence of maybe a second impactor population as been proposed in the past, but these counts are actually still pretty preliminary, so I don't want to say that it's not there just because I haven't seen it yet. I need to finish my work. And the difference between these two plots is this one's a little bit busier and the error bars are larger because these are all counts from smaller high-resolution images, which provide great data for these smaller crater range, smaller diameter ranges. But since the areas are smaller, you're not getting as many craters counted, so your error goes up in the statistics. One exception we see is Enceladus, shown by the black curves, which seems to have a steeper drop-off for diameters greater than about 6 kilometers and diameters less than about 2 kilometers, as shown by the changes in the black curve relative to the other curves. And this might be, the small end might be due to burial, or is this in fact the different impactor population I was discussing? I personally don't think so, because we haven't found evidence for it yet on the other bodies, and we should, even if they are heavily cratered. And there are some younger terrains on these other bodies that, although I've only counted small portions, don't yet show the evidence. The larger craters may have been viscously relaxed away again, or again, we could be seeing the other impactor population. Also, Phoebe seems to be different. Phoebe is shown by the orange curve in this plot. Phoebe has this dip around 1.5 kilometers that is not seen in any of the other satellites. Phoebe, however, is thought to be not a regular satellite of Saturn, but was captured at some point, maybe early on, maybe later. And its distribution may be more a representation of the distribution on these very small bodies that are actually not even spherical. They're a regular shape. They've been bombarded and broken up. So this may be a different view of a different population that's not affecting any of these other larger satellites. Something else we can do with this crater data is actually plot it spatially. This is the data within the cratered plains on Enceladus. The rest of the surface here, which is not part of this plot, is actually what we call ridge plains. They're very young surfaces that have been highly resurfaced, tectonized, possibly cryovolcanism. And of course, at the South Pole, we have plumes coming out, and basically escaping ice and water at the South Pole. And this area all down here around the South Pole actually has no visible craters, so it's a very young surface. But looking into the crater plains, or the older areas of Enceladus where there are lots of craters, we have found that even there, the crater density changes with latitude. It's higher at mid-latitudes than it is at the equator, and this might be telling you something about a process that is removing craters at the equator. Here again, some counts from Saturn's moon Dione, where we're showing counts from slightly different terrains. We have counts from the crater plains unit, or basically the units that's the most heavily cratered. And then there's another unit on Dione that's slightly less heavily cratered, called smooth plains, because they look very smooth on the image compared to the battered up crater plains. And we find that the shapes again of the crater distributions are comparable. And this might be implying that the impactor population did not change over the time frame of the oldest surface to when it was resurfaced to create these smooth plains. So to quickly run through some comparisons, I haven't talked much about Uranus's and Neptune's satellites. because although we have imaging of them, it's from Voyager back in the early 80s, and actually I think Neptune was in the late 80s. But it's not the best resolution and not the best coverage, so we haven't been able to learn a whole lot from those yet. But hopefully, if we have another mission sometime, that we'll be able to learn a little bit more about those satellites as well. But some of there was some preliminary work done with those, and they can be used a little bit to compare, as I will mention. But unlike past work, I found that the size frequency distribution is similar between Saturn and Jupiter satellites. So we have Callisto as a proxy for Jupiter satellites, and then here's a curve that I've generated for Saturn satellites. And they seem to be similar and not different as what was found in past work. And this implies that there's been one primary impactor population for the outer solar system. This is further supported by the fact that Uranus's satellites also appear to have similar size frequency distributions to Jupiter and Saturn's. The crust of the icy satellites seem to be generally layered in some way, with bright and dark material often alternating, as evidenced by the bright or dark ejecta that's brought up and surrounds craters. Central pit craters are common on Ganymede and Callisto, but not on any of the other satellites. So the formation is likely a strong function of gravity, because these are the biggest of the satellites discussed, and it may rely on a warmer lithosphere, which these are also thought to believe to be had. Multi-ring basin structure varies from surface to surface, and it's dependent, therefore it's thought to be dependent on the rheology of the interiors of these satellites. So basically, again, how thick is that ice shell? Is there warm ice underneath it or water underneath it? So the impact craters are telling us something about the interior. And again, we find that some of the bodies have been more recently active than others. Enceladus and Io have current activity. Europa, through dating, is thought to be the surface no older than about 60 billion years. Or that should say million, I'm sorry. 60 million years. Ganymede is the activity on Ganymede occurred about 2 billion years ago. And the smooth plains that were found on Dione are also seen on Tethys, and they're thought to be approximately 4 billion years, formed 4 billion years ago. So now we can actually compare the inner solar system to the outer solar system. And when we plot the Saturn system and Callisto with the crater density population found on the moon, we find that these size frequency distribution shapes are not similar, implying different impactor populations for the inner and outer solar systems. And since we've already discovered that the inner solar system is likely impacted by asteroids, that means the outer solar system moons likely are not. They're probably more impacted more often by comets from the Kuiper Belt. But we don't have good enough data of the distribution in the Kuiper Belt to know for sure if that's the case. Simple craters, the simple bowl-shaped craters, have similar depths on the rocky and icy bodies, implying that the crater mechanics is the same on those two for the gravity regime in which simple craters are made. Complex craters are generally shallower on the icy bodies, implying that the modification is different depending on the rock, ice, and gravity, since, of course, many of the moons are smaller than the planets, although some of them are slightly bigger than like Mercury, so in that case it's probably more compositionally dependent. The transition diameters between simple and complex craters generally occur at smaller values for icy satellites than rocky bodies, and this is most likely due to that ice is just generally weaker than rock. And we have these central pit craters in the outer solar system, and they do occur rarely on Mars. And at the same size on inner solar system planets, the peak ring morphology usually occurs. So this difference may be an implication of water in the rock or just water ice rheology being different and this size crater, for this size, particularly sized crater on these surfaces. So to conclude, impact craters are a common geologic feature in our solar system, and studying them has provided and will provide many important insights into a wide variety of questions about our solar system. Some bodies in our solar system have been recently active, and we can date some of these surfaces. The gas giants likely underwent a major migration of the orbits in the early solar system history that led to a heavy bombardment of the inner solar system. The inner and outer solar system have been impacted by different impactor populations, mainly asteroids versus comets. And at least I think so, the physics of hypervelocity impacts is pretty cool, because these are objects that are moving really fast and creating very large explosions that we only barely understand from the small explosions we can make here on Earth. Some open questions, and this is just a few. There are many questions that remain to be answered. So is there a different impactor population for old and young terrains in the inner solar system? Some have claimed that they have found that when they count craters on like the younger surfaces such as the Mare on the Moon or some of the younger surfaces on Mars, that they see a different distribution shape than for the very old surfaces. And they believe that this might be due to this younger population actually being near Earth objects and not directly from the asteroid belt. But some say no, they look exactly the same. So what it might take to resolve this argument is just another person doing counts, generating another data set to see if maybe either of these groups have some bias in their counts. Are there two impactor populations in the outer solar system? As I mentioned, I have not seen it yet. Researchers in the past thought they found one. It is likely that there is another set of impactors, especially in the Saturnian system, where we already see them forming rings. But just more data needs to be generated to understand this. Is contamination by secondaries considerably affecting crater counts in small diameters? There's a group that argues yes, and there's a group that says no. So, again, just counting something that we can use to tell secondaries from primary craters often is what their depth is, because as I said, the secondaries aren't formed as by high energy as an impact, so they might be shallower than their primary counterparts. Until we can actually maybe get very high resolution images or even go to some of these surfaces, we may not be able to truly answer this question. What is the cratering rate for the outer solar system? In a couple slides back, I gave some ages for some of these surfaces of the outer solar system satellites. And this was based upon a cratering rate generated from past crater counts, from observations of probably just maybe 3 impacts in the time that the outer solar system has been observed. And these have all been fairly big impacts, because that's all you can see. One of them being Shoemaker-Levy 9. The very sparse data we have of what the Kuiper Belt looks like and its crater distribution the size distribution looks like. So we don't really have a good idea of what the rate is, and we just need lots more imaging to understand this. And the rate we discussed for the lunar chronology for the inner solar system, is it truly determined? Apollo only visited 6 sites, so we only have true data from, we really only have 6 true data points. And so can you actually determine a curve for 4.5 billion years from 6 data points? What specifically are the causes for the morphology differences between the inner and outer solar system? Mainly, why do pit craters form in the outer solar system and we do not see them in the inner solar system? And why and how just do the different morphologies develop? Why do we see peaks? Why do we see pink rings? Why do we see multi-rings? So that's it.
Question. You talked about the inner solar system and outer solar system impact rates being caused by different things. Is it possible that it could just be one function that's like distance independent, distance dependent from the asteroid belt? Like inside the asteroid belt, you have one function. Outside, you have a different function, and it could be different on a different rate on Mercury than it is on Mars, and then outside on the other side, it could be different on around Jupiter than Saturn or something like that.
Yes, and there are people that argue for that. And actually, for the inner solar system, we already know that to be true. You have to adjust the rate for the distance, and actually also for the gravity, which is the most important thing. A body as big as, like Venus size is going to actually attract more impactors than a body of Mercury size because it just has larger gravity well. And so you have to adjust for those factors when you're looking at a lot of these things. But the case for having asteroids move out into the outer solar system is one that people try to argue for. I am, however, skeptical about the arguments, mostly because dynamically it's very hard to get the asteroids to go towards and past Jupiter, basically. Jupiter likes to kick things in or kick things like way out, even vertically out of the plane and all that kind of stuff. So, I mean, it's dynamically. I've talked to dynamicists about this, and they just don't think that it's likely for asteroids to come out of the asteroid belt into the outer solar system. It's just not. Jupiter just causes too many issues with that. So, but it's, I'm certain that some asteroids must get out there sometime, and that does throw a wrench into what we think the rate might be. And, but at the same time, you're going to have comets that occasionally come into the inner solar system. So, and there have also been models done of trying to take the asteroid belt population, the curve that's generated by that, and make impacts on, say, like Callisto, and see if it matches what we actually observe, and it generally does not. So even adjusting for gravity and velocities and moving things out there, you just can't get the same shape. So they think that there truly is a difference in the two populations.
One of the original pictures you showed an asteroid or craters on an asteroid itself.
Yes.
Now, what's the chance of that happening? I mean, is it part of a big system in itself when it got hit, or does it happen when it was a small body?
Well, the craters that you see primarily had to happen after it was already a small body. Although if it was broken from a larger body, some of that surface could have been previously formed when it was part of the larger body, if it shows the old surface. But
You showed three on one of the pictures, three dimples on the surface. Which is a pretty remote possibility, isn't it, happening under the normal circumstances, like the planets?
You mean just
Such a small body.
Yeah. The rate goes down, but many of these surfaces are thought to be very old. When, as I showed in some of those movies, the asteroid belt they believe used to be very heavily populated with asteroids, and so they would all just constantly be running into each other. And but that was back 4.5 billion years ago. And of course, now we know that the picture is much different. They hardly actually run into each other now. But if the surface is old enough, which we think they are, then they could have been formed back when it was much more densely populated.
Is there any way to tell what the impact velocities were?
That made the craters? In a way, the physics does allow you to back that out of the size of the impact crater, but you have to make a lot of assumptions about how big because it's dependent on how big the impactor was and how fast it came in. So you have to know one or the other to figure out the other. And we often don't know either. So you have to just kind of make assumptions. And actually what's more often made is the assumption of how fast it came in, because we can know something about that from the fact that we know how fast gravity will pull on that object as it's approaching the planet.
Depending on where it comes from, right?
That too. And the assumption is generally that it comes from infinity, which of course isn't realistic, but that's generally what we have to assume. And so we do the best we can with the knowledge we have. So.
My name's Alex Monchak. I'm in the engineering management program. And it just went away, so I was going to ask. My question was about the... Oh, there it is. Okay, this is actually the top open question. My question is, how does your field document the counting of craters? Rather than having somebody do an independent count, look for bias, is it customary for your field to share the actual, however you actually, show that this count is, and you put a mark on the chart and says this one's this and this is how I determine it? And is that the philosophy? And do students in the physics program here have an opportunity to do master's thesis work with LPI in this area?
Yeah.
Yeah, he might actually know better than I would about the second question. I know that we're trying to get more collaboration going with students here and with the LPI. If a student is really interested in counting craters, I could certainly show them what to do and how to do it. As for the first question, ideally what you described would be what we'd want to do. Basically, everybody would be able to see exactly what the other person counted and what the size of it was that they counted, because sometimes people make measurements from different parts of the crater. Like I typically measure from rim to rim, but some may choose to measure, somewhere else. And these are all part of the statistical error that goes into these calculations, which I think is actually sometimes not large enough, the error bars we show, but that doesn't happen usually. Usually all we have is mainly the plots that I've shown here, the R plot format, where we can compare our counts to somebody else's counts. And if they fall together, we're assuming, okay, well, we probably did it about the same way. We both have similar idea of what's a crater and what's not a crater. And so you have to say, okay, so if two independent people came to the same conclusion, then hopefully they both did it mostly right. It's when we have conflicts, like the first question is part of that. These two people don't see the same thing. So what does that mean? Who's wrong, or is anybody wrong? Maybe, maybe they just see craters differently, and in that case, what you need is just another independent counter and another one. And ideally, you'd have, thousands of people out there counting the same area to get the true statistics of the region, but we don't. We have, I'd say there's probably maybe a dozen of us doing this, and we're all doing different terrains. And so, it's like, I am doing the outer solar system right now, and there's basically one other group headed by this guy, Gerhard Neukom, who's in Germany, doing the outer solar system. He also has a group doing counts on the inner solar system. And then there's a few people also doing counts on the inner solar system, such as this guy and this guy here. So what we have is a system that's not really sharing the actual data right now, but sharing the final product, and we're trying to determine from the final product if we're all agreeing or not. So.
What about the composition of the impactor? Is that not enough of a factor, or we just don't know much about it?
Both.
Okay.
Generally, the strength of an impactor which is dependent on the composition usually, is not as big of a factor in what the crater is going to turn out to be. Mostly because it's it's mostly destroyed in the impact, no matter what it is. Although, when you look at impact craters on Earth, you generally see more of the remnant impactor if it was a stronger material, such as an iron meteorite, than if it was a rock meteorite or a comet. And there are arguments that, especially the difference between some of the rocky, like asteroid compositions, might form very different craters than the comets do, because they're mainly ice, and so they are definitely a lot weaker. But people aren't sure yet, because we don't know enough about what happens with each one, which is the second part of your question, is that we just really don't understand also the effect of the composition, because we don't have enough data. We don't really know most of the time what kind of impactor formed what crater. So.
I imagine due to the high speed and the tremendous energy from that speed would make that a lesser factor.
Yeah.
Do you expect to have more data to be visible?
Possibly. I mean, I would think if you'd go anywhere that had a lot of craters, you might find more remnants. Because, as I mentioned, here on Earth, we only have 150 data points, and some of them are so altered that you're probably never going to, if it even lasted, you're never going to find what the impactor was. But going to places like the Moon or Mars would definitely give us more data points, and just bigger numbers, so you're more likely to find those scattered points where the impactor remains. Yes?
Can you use in processing software, pattern recognition software to do these counts?
There are people working on that, and so far a successful algorithm has not been developed. Those that are even semi-successful need some kind of topography. So you can't just use some of the images I've shown here. You actually need to know how deep the crater is, and well, you don't need to know how deep, but the algorithm needs to see the depression basically in 3 dimension, rather just by shadows or something that our eyes can tell.
Circles and rings.
Yeah, and there are people working on algorithms just to recognize circles. The issue with that is that lots of things are circles, not just impact craters. So you still would need a human to go back and say, that's an impact crater and that's not. And
The one on the Moon would not be an impact volcano, perhaps.
yeah, and yes, there's not many very big volcanoes on the Moon, but there are things that we see that might be vents, old vents, that would be circular depressions, and we see actually the other main thing, and this can actually is true of most of the bodies, is that just collapse pits can form. Basically, sometimes if you open up a small crack or something, the regolith, which is very common on these satellites or on these bodies, can drain into the crack and form a little pit, and all it looks like is a pit from the surface. So those are some of the other circular features you might have, but they're smaller, so you might be able to use it for a certain diameter, size, and bigger, that nothing could be as big as this except for an impact crater. So, but yes, and the short answer is there's people working on it, but there's nothing concrete yet that can actually do what I do. So, or what any.
The best equipment is an army of graduate students.
I've heard that from many people. Yes, I get a summer intern. That's all I get. So, yes.
What about the Kuiper Belt? It doesn't seem to be mentioned very much. Do we not know much about it, or is it not as much of a factor?
Well, most researchers think that the Kuiper Belt is the source of impactors for the outer solar system, so the source of the comets for the outer solar system impacts. But we don't know enough about it to know for sure if that's the case. Like, for example, in the inner solar system, we actually have fairly decent imaging of the asteroid belt, and we know what the diameter distribution is somewhat for the asteroid belt. Kuiper Belt, we have nowhere near even what we have for the asteroid belt, and that's because we can only see objects right now, certain diameter and larger, and so we have no idea, what the distribution is for. I don't know. I'd say off the top of my head, probably smaller than maybe 500 kilometer size. So I mean, and and that creates a pretty big impact. And,
So we have no physics information saying it isn't a factor. We just don't know.
yeah.
Anything about the distribution pattern that tells you about same age material or what do you work from?
So if you're counting craters like on the same age surfaces of different bodies, well, like I showed with some of my Saturn data, if you can compare them, and if they all seem to look the same, then you might be able to say, well, it's likely that the same population of bodies is the impacting source for that system. And that's partly how we came to the idea that the asteroid belt is likely for the inner solar system, because we see all the same pattern in all the heavily cratered parts of that. And I'm starting to see all the same pattern on all the heavily cratered systems in the outer solar system. But it's a different pattern than the inner. So that's why we're thinking that it might be two different sources for the inner solar system and the outer solar system.
Do you see any shielding going on from other objects?
Not so much, no.
Not so much. Anything different distribution here?
No, the bigger difference actually comes from, especially on satellites, comes from the leading and trailing hemisphere. So the leading hemisphere is, of course, the side that's flying into the orbit. So as you're moving around, the leading side would be the side, and the trailing side is the trailing. And the leading side seems to collect more impacts than the trailing side does for satellites. I don't know that they've seen this on planets, because I think they're generally bigger and it's not as much of a concern.
But if they're rotating,
I guess more burns at the
doesn't it spread it out over the...
Yeah, and that's why you don't see it on planets.
Well, moon,
But on the moon, which is synchronously rotating, it's always facing the same side as it's leading and trailing. So
Mercury has a certain 3-2, is it?
yeah, but I think there's enough rotation that it won't see it either. So
Does the word cloud contribute any?
that's a good question. I think most people, I think that it's generally agreed upon that the Oort cloud probably does not throw in enough material to make a significant source of impactors.
We have a passing star that disturbs it at some
Then it
point.
might, yeah. So
Has that ever been, I thought I read something.
I don't know that it's been examined as the case for creating an impact type event, like maybe the late heavy bombardment or anything like that, but I'm sure it's been examined just by general dynamicists who are interested in what it might have happened or what may happen to our solar system if these kind of events occur. So.
Okay, let's thank our speaker.